Hi, welcome back to the Thin Films course. My name is Professor Carlos Tavares from the University of Minho in Portugal. And so this final chapter will be about chemical vapor deposition. So the techniques of chemical vapor deposition, CVD, normally they employ a volatile compound containing the material to be deposited. So it contains a precursor gas normally, which will chemically react with other gas inside the CVD reactor. By this way, a non-volatile solid is deposited with a very controlled way, and precisely monolayer by monolayer, or also can be deposited in the type of clusters of atoms. And normally it's on a heated substrate at a specific temperature, which is that's T sub. So the various CVD processes differ between them. They can be, for example, atmospheric pressure CVD or high vacuum CVD or hot wire CVD. And normally these CVD processes, they differ between them on how the activation energy is supplied to the reactants for the formation of the precursors. So that we have some reactions on the surface of the growing front of the film or on the substrate to form this non-volatile solid, which is deposited one layer by one layer. And so normally this activation energy is either given by light, by electromagnetic field, or for example, you can use a radio frequency generator, or you can use plasma, etc. So I'll be showing you some, or even a hot wire process, which is more simple. So I'll be giving you some highlights about these different CVD processes. Here on this example that you see here, it's very common. It's a plasma enhanced CVD system, which means that you have to have this process gas, which is the precursor gas, which brings the material, the raw material that you need to put on the surface of your substrate. Okay. Normally, this precursor gas can be very complex, but we will only look at what we really want from this molecule. And the transport of this process gas has to be done by an inert gas, which transports the process gas close to the substrate. Normally, the substrate is heated, like I said. And in this particular case, as the process gas passes through this channel here, we have a radio frequency power generator, which activates the plasma and breaks down the precursor into other types of molecules, which can be absorbed on the surface of this heated plate that you see here. Okay. There is something similar to CVD, which is homoepitaxy and heteroepitaxy, or vapor phase epitaxy, which is used to produce monocrystals, for example, not particularly thin films, but monocrystals. For example, chemical vapor deposition is a technique that's widely used in the industry for the deposition of thin films of various materials. You can, for example, produce semiconductors for LEDs. You can produce TFTs. You can produce LCDs, OLEDs, for these new screens and for cell phones and for TVs. You have seen all these big, very big OLED TVs already on sale. And they can be, these films can be in the form of carbides, nitrates, oxides, or simply a single element, such as amorphous silicon, which can be used for photovoltaic cells on polymer substrates. Amorphous silicon is different from crystalline silicon because amorphous silicon is transparent, whereas polycrystalline and monocrystalline silicon is opaque, to at least in the visual range. And so it means that this amorphous silicon can be used as transparent photovoltaics for transparent photovoltaic panels, for example, to functionalize in clothing or other surfaces. Okay, so most of these films find their way in micro and macro electronic devices, as well on protective coatings, such as in the case of DLC, which is diamond-like carbons, which is very useful, for example, for the car motor industry, where you can produce coatings which have a very low coefficient of friction in order to prevent the wear of the mechanical parts of the motors. So, as I mentioned before, there is a variety of CVD techniques for the growth of monocrystals, large crystals, which are very periodic and are very ordered, which is called vapor phase epitaxy, VPE. This method is used for the formation of epitaxial crystals, so crystals that grow very well orientated with one whole grain, which is we can consider it infinite, but of course you don't have infinite crystals, but it means that you will not be producing polycrystalline material. And it's isostructural with the substrate. Normally you have to produce the material on a substrate. You have to grow this material on a substrate which has the same crystalline lattice parameters, okay? For example, AbO3 types of materials with a perovskite structure. And if they are really isostructural, they have the same structural parameters at the beginning, then we call it homoepitaxy. If on the other hand, if they differ from the substrate, then it's called heteroepitaxy. And normally this is done at very, very high temperatures, okay? So this monocrystal, which means above 600 degrees C. So these monocrystals are formed from reactants that are the source of the atoms or molecules to incorporate into the crystal. So you also need these kind of precursors. For example, it is used for the growth of silicon, gallium arsenide, gallium nitride, and silicon carbide, among other types of monocrystals. It is not common to refer to these materials as thin films because they are large monocrystals. So let's look at the CVD process, okay, in general. And like I said, you need some source for the activation of the precursor to break down the molecule, so you can break down into its constituents that will react on the surface of the substrate and on the growing part of each monolayer that you are depositing on top of each other. And this activation can come from heat, from radiation, from plasma, or from a hot filament. For example, you can have, for example, a hot filament, which you pass a very high current. And for example, when a methane gas or hydrogen gas passes through the filament, if the temperature is high enough, above 2000 degrees C, then this heat can break down the molecules. For example, you can separate the hydrogen from carbon in methane, or you can break down the hydrogen molecule into atomic hydrogen, for example. For example, if you want to make a heat treatment in a reducing atmosphere, okay? So in these type of processes, you normally have reactants, which come into your reactor in the form of a gas. So we call these the precursor gases. Then you have activation energy, okay? So you want to break down the reactants. Then you have the growth precursors, which are gases. Some of them can condense and be part of the material that you want to produce, or they can be taken away by a carrier gas after each monolayer is deposited. For example, in a particular method of CVD, which is atomic layer deposition, you are producing pulses where you have a pulse for bringing down the precursor, then you have another pulse to bring another gas that will remove the secondary products or the non-reactant products from this reaction. And so from this reactant's positivation energy, you will have the growth precursors in the gas form and secondary products in the gas form. Then you will have heterogeneous reactions on the surface of your substrate or of the atomic layers that are produced. And then you will form a thin film, and you will need to desorb the non-wanted products in the gas form, which will be taken away through a carrier gas. So this image is really very useful to understand the whole synopsis of CVD when you're trying to produce a thin film. So let's go step by step. So we have to have the transport of the raw material, which is the processed gas or the precursor gas, okay? And it has to be taken onto the substrate. Imagine that you have a molecule which has this big blue ion with small red ions, okay? But you don't want to make a deposition of a material which has the red ions. So you need to have some kind of way to desorb them, okay? So first you transport the whole molecule, the precursor, onto the substrate, okay? Then there should be some absorption or chemisorption kinetics of the precursors on the substrate and the subsequent film pharmacy. You need to have some kind of a way to produce this absorption or chemisorption, for example, through previous generation of radicals on the surface of your substrate. Then you have surface heterogeneous reactions, which, for example, will lead to the diffusion of these species that you want to nucleate on the surface, and to the desorption, to the removal of the other items that you don't need in the chemical process. Okay, so you have diffusion of the atoms and molecules on the substrate film that you see here, these blue ions. Okay, you have nucleation and growth according to the kinetics of growth that we have seen in the previous chapter. Then you have the desorption, or the removal of secondary products by a carrier gas, which are taken away, for example, into the atmosphere or through another exhaust system. For example, let's look at what happens when you want to produce amorphous silicon, which is hydrogenated, which is interesting for producing transparent silicon films for photovoltaics. So you really need to have a precursor, which is silane, which is this molecule Ch4. You have to have provide some kind of activation energy, either by heat, which is this triangle here, or by photon, by light, or by electromagnetic field. Okay. And when you provide one of these steps of activation, you will break down this molecule into under stoichiometric, for example, SIHX molecules. And you further add oxygen, you'll have the formation of other compounds between silicon and hydrogen, and with oxygen. And so you will have these kind of gas phase reactions, and then you will have also gas surface reactions and surface reactions here for the formation of the film. You'll see that it's really important, if you want to have a hydrogenated silicon, you have to provide these molecules that have the radicals that either will make the bonding between silicon and hydrogen, and also silicon with all H groups. And afterwards, you can remove part of this excessive hydrogen and oxygen, but due to the fact that these radicals that you see here, for example, you have a hydrogen here radical and an OH radical, they can just form water and be taken away. So for the best thin film quality, you need to have a high concentration of radicals with low adhesion. That's what you see here, or co-dissociation coefficient. You have to have so low concentration of these radicals, but a high concentration of these radicals here on the substrate, so they can trigger the adsorption of silicon and the bonding of silicon to the substrate. So you have to have a low concentration of radicals with a high adhesion coefficient. You have to have a high surface coverage of hydrogen, so you can promote this hydrogenation with silicon. Then you have to have a high surface mobility of the precursors. So these precursors need to have a high mobility on the surface. Okay, so they can make a full coverage in this particular case of silicon on the substrate. So let's take a look at silane or silane. Silane is a chemical compound with a formula SIH4. This chemical formula is analogous to that of methane, which is CH4, but albeit it's derived from silicon. So silane is a very complicated gas. For example, if you have a CVD reactor which uses silane, normally you have to have a detector for silane, because silane has a problem. If silane is exposed in the air, it can break down into a spontaneous combustion, and it can be very dangerous. So you have to have detectors if there is a leak of silane that can warn you that you have this kind of leak. On the other hand, if you heat silane over 420 degrees C, then it decomposes, okay? And then you can decompose silicon, you can decompose silane into silicon hydrogen atoms, or into other stoichiometric forms of silicon and hydrogen. So let's look at the radical formation from silane, depending on the activation energy. If you give a high activation energy or a low activation energy. So if you give a low activation energy, you break down silane into SiH2 plus hydrogen, and this will cost about 2.2 electron volts. If you increase the activation energy to 4 electron volts, then you can break down SiH4 to SiH3 plus hydrogen. If you have sufficient energy, but greater than 4.0 up to 4.2, then this will benefit through the breaking of the saline and forming silicon on the surface, as you see here. Okay, but you have to give this has a cost of 4.2 electron volts, and in this form you produce the silicon, and you also produce this important hydrogen radicals that you have these bonds here with silicon, which are important to continuously nucleate silicon on the surface, have a full coverage, and then create subsequent layers on top. And the equation that generates or that controls this radical generation is given by this expression Gx, and x is just one of the directions of the coordinates of your sample. You can, of course, the same applies in the y direction, but let's just take a look at one direction, in the x direction. So Gx is the radical generation rate, which you see here on the surface, okay? And it's obviously it depends on the position, because you want to have, for example, for the case you need to have low concentration of radicals with high adhesion coefficient that will entrap the silicon on the substrate, and so this low concentration has to have high adhesion coefficient, and you can calculate the rate of creation of these radicals along this direction. Imagine this is x and this is y, okay, x and y, by just simply calculated equation according to x. Here d is the diffusion coefficient, and the small n is the concentration of the radicals. K is the reaction speed of these radicals. Okay, we will take a look at this K, which is important for understanding this process of creating different types of reactions, starting from saline. And this N here, the capital N, is just the concentration of the molecules of the gas that you have, the precursor gas that reaches the substrate. Okay. On the surface of the film. So let's take a closer look at how we can interpret this equation. For example, for plasma enhanced CVD conditions, where you need to have a plasma to break down the precursor, in this case the saline, when you activate the saline with the plasma, this saline plasma consists about 99.9% of SiH4, and only about 0.1% in radicals. So most of what you have close to the substrate is actually SiH4. So hence all the collisions are between silent molecules, because they are a much larger concentration. So the concentration of radicals, which is this N here from this differential equation that you have here. So the concentration of radicals that are formed at a given point, if you, for example, start at x equals 0 and continuously calculate the generation of radicals along x direction. So this concentration of radicals can be calculated by this exponential function, where you have a pre-exponential factor, and here in the argument of the exponential we have minus x over r. X is the position of the radicals along the x-axis, okay, and k is the rate speed, or the reaction speed of the radicals, and then is the concentration of the precursor molecules in your chamber, okay? And so this concentration of radicals that are formed at a given point, they can be really calculated as a function of the whole distance on your substrate, and you can just integrate the last part of this equation by considering Gx equals to 0, and then you will have this equation, this exponential equation, which will gives you the concentration rate of the formation of radicals on the surface. So if you have a uniform plasma, okay, and don't forget that it consists mostly of saline, so the initial concentration of the radicals is actually this pre-exponential factor, this N0, and this is equals to G times tau. And where the lifetime of radical before reaction is tau. So here you have this is the lifetime of the radical before its reaction on the surface. And this rate of reaction or this lifetime of reaction, it has to be inversely proportional to the reaction rate, which is K, times the number of molecules or the concentration of molecules of the gas precursor that you have. So, but then we can understand a little bit better these different reactions that you see here, okay? Because, for example, so if you have radicals with a higher reaction speed, and this higher reaction speed have to be those here, which can be removed easily, into, for example, transformed into water or into hydrogen that you see here, which have a low adhesion to the other elements here or to the other radicals, then K has to be very high. So which means if K is very high, then this lifetime is very low, okay? And this is what happens, for example, when you break down SiH4 into SiH2, okay? With a very low activation energy, okay? And vice versa, if you, on the other hand, for this case here, where you have a high activation energy, and you, for example, you will need to have these silicon radicals here, which have high surface coverage and a low concentration and a high adhesion coefficient, then the lifetime is very small, so you have a high reaction rate. So let's take a look at the benefits of the CVD process. For example, when you compare to the physical vapor deposition or PVD process that we saw in the previous lectures. As I mentioned before on the previous lectures, sputtering, for example, or evaporation, they have their limitations. They can provide very good coatings, specifically for example, for optical coatings or for mechanical properties coatings. For example, you want to have coatings which are mechanically very strong, with very high addition to the substrate, very hard, or they are very rigid with a very high Young's modulus. But there is a drawback from the PVD processes because of the conformation. It means that, for example, if this gray layer is the coating, and if you want to coat a subject which has some pores or protrusion or dimples or this kind of values that you see here, then sputtering is not the best choice, or thermal evaporation, because it will not give a uniform thickness throughout the whole structure of your substrate. Okay. So it's not conformal. You will not have a very good conformity with the shape of your substrate. On the other hand, CVD processes, they take into account that if you can generate the radicals across these whole steps of the surface, then you will have a uniform production of a thin film or coating on the substrate, which is conformal. And in most cases, you will have a dense microstructure. You will not have this columnar structure that you saw, for example, in some coatings produced by sputtering. Okay, it has a relative low cost of operation. It really depends on the cost of the precursors. Okay, and it has a large scale production. So you will see the different types of CVD process, for example, for the production of microelectronics. For example, for the MOSFET devices, there's a slight error here. So the world share of integrated circuits, ICs, so you'll see that MOSFETs represent about 88%, bipolar transistors about 8%, and group 3-5 element semiconductors is about 4%. And take into account a chip, for example, in a computer, you might have 1 billion of these devices per chip. And so this is, of course, is an amplification, for example, of a MOSFET device, which is like a transistor, where you will see that you have different types of materials. So you need to have first the substrate where you're going to put your MOSFET device. Then you have to make by CVD the deposition of the implant, the electric materials, the insulating oxides, for example, silicon oxide. And then you have to put your dielectric material, which is the active part of this MOSFET. And on top, you have to put the electrodes. Normally, these are metallic electrodes. This can be done by sputtering or thermal evaporation. But for these insulators, the implants, and the electrics, which are normally oxides or nitrides, you will have to produce them by CVD processes. And here you can see the scanning electron micrograph of a MOSFET, and you will see, normally as you'll see in the transistor, the source, the gate, and the drain, which are the three essential parts of this device. So let's look here at, for example, this MOSFET transistor. And the MOSFET, it's an abbreviation. It means it's a metal oxide semiconductor field effect transistor. And this was developed in the early stages by Julius Edward Littlefield in 1925. And here is what a modern MOSFET looks like, okay? And you need to have, you have to start from a substrate. Normally it's crystalline silicon p-doped wafer. With p-doped, it means that it has lack of electrons, so you have a surplus of holes on your substrate. Has to have a positive charge on the surface. So you'll start off with this kind of substrate. Then you will make the depositions for the insulating parts that you saw here, for example. These insulators, which can be SiO2, silicon dioxide. Then you will have the polysilicon deposited by CVD, and the dielectrics also silicon dioxide or silicon nitride, also formed by CVD. And then you'll have aluminum for the contacts on the gate, the drain, and the source, as you saw here in this schematic. And of course, in order to produce this complex material, you have to have masks where you do these layers sequentially. You perhaps have to do some chemical etching or ion etching to remove some parts of the layers, so you can have this actually complicated layer structure. So let's see how we can, for example, produce the TFT. And you know, TFT, it's those kind of transistors that you have in the large number of televisions that you see on the market, which are not OLED. You still have TFT. If, for example, if you have a mobile phone, or if you have a laptop computer, then the monitor should be, in most cases, a TFT. And the new ones will be, the most expensive ones can be OLED. But the TFT, it's actually abbreviation for thin film transistor. It operates like a switch, which turns on and off depending on the gate voltage that you saw on the previous schematic. So you can have TFTs which are bottom gate, or can have a top gate. This is more, we're going more into microelectronics, which is not my scope for this talk, but it's only an example just to show you how you can produce different types of layers of materials to produce a device. And you can do this by a combination of methods, by CVD for the oxide materials or the nitrides, and by sputtering or thermal evaporation for the electrical contacts. And so we'll start off with a substrate. We'll choose a substrate, for example, silicon substrate. Then, for example, you can produce the metal contacts here. For example, for the gate, if it's a bottom gate, then you have to put a whole layer of aluminum, okay? But you cannot short circuit this gate with a source or with a drain. So afterwards you produce a whole layer of gray material. Here you see yellow, but before producing this yellow material, you have to have a whole layer of metallic aluminum, which afterwards you have to have some form of masking the gray parts in order to, by chemical etching, to remove these parts here. Then you will have the deposition of the electric material, which is silicon nitride by CVD, then amorphous silicon, and on top hydrogenated amorphous silicon, which is p-doped, which has a positive polarity, or it's doped with holes. It's not n-doped. And the same thing applies for top gate TFT. Instead of having the gate here on the bottom, you can have it on the top. But the same process, the same, well, a similar process is developed. You first you make the contacts, you will do some matching. Then you reverse the order. You start with this P-type hydrogenated amorphous silicon. Then you will go into the normal amorphous silicon, the dielectric silicon nitride, and then on top you have to have electrical contact for the gate. So we can do this by a sequential production sequence. See here, but here you can see, you can after take a closer look, you can see how it looks from the cross section and from the top. So you will have your substrate, okay, and all the layers that you will put on top. He will have an idea of the thickness of the layers. So normally the aluminum metal contacts are around 150 nanometers or 1,500 angstroms. This yellow material, which is the electric material, the silicon nitride, can be about 300 nanometers, and the silicon layers are in the range of 50 to 20, from 50 to 150 nanometers, one of them, the other from 20 to 30 nanometers, okay? And for example, if you take a look on the, if you want to see how we can produce these layers here, then you need to start with your substrate, and you will make the deposition of the metallic layer, as I told you, the aluminum layer. You cover the whole surface. Then you have some kind of chemical etching to remove this part. You just put a mask here on top to preserve this layer. Then you gradually start doing adding the layers with successive masking and also etching steps, so that in the final you have this structure of the layers as you see here. So it's a heterostructure. Either for the bottom gate or top gate, you produce the same. And all these processes are performed by CVD. But the first process, which is the metallic layers, they can be produced by sputtering or by thermal evaporation. Then you will have, for example, a device, for example, for the case of the white LED. For the white LED that you have, for example, in the newer lamps that you have in your house or at school, etc., or in your car, you see that you start off, for example, with a base material, which is your substrate, can be glass. In most cases, the gate electrode is molybdenum. Then you have a gate insulator, which is a combination of silicon oxide and silicon nitride. You have your active material for emitting light, which in this case can be, for example, zinc oxynitride. Then you have the source and drain electrodes, also can be molybdenum. And then you in this way, you can see also from this cross section that you have the different layers and you can produce this device. And normally if you want to check if the device is working properly, you have to do these kind of experiments. I'm not going obviously into this. You can take a look at this paper here. But for example, you're just measuring the current from the drain to the source. So you're measuring the flow of charges from the drain to the source, the S, okay, as a function of the voltage that you apply between the drain and the source as a function of this potential. And you have this kind of curves. And these curves are produced for different voltages between your gate and your source, okay? So you can take a look afterwards at this paper if you like to see how you can produce this type of devices. Now let's see one of the first atmospheric pressure processes. It's AP-CVD, so atmospheric pressure CVD. You don't need vacuum. And normally you just use this to treat silicon wafers. So in atmospheric plasma CVD, the reacting gases, they enter here through the top. So these are the process gases, and normally they include hydrogen, water vapor, or oxygen. And these process gases are fed onto through here to the substrate. You don't have any activation part here. The activation is only on the surface of your substrate, and it's by temperature. So the heat will provide activation energy to break down these gases and transform them into radicals. And then you have a transport gas to transport this process gas closer to the surface of these wafers. And so normally in industrial application, we have this roll-to-roll system where the substrates are just fed under this reactor here, and both all gases, the inert gas, which is a carrier gas, and the process gas are just fed onto the surface of these wafers. And normally you do this so with this transmission belt, and you have an infrared heater which can heat the substrate between 300 and 900 degrees, and so this is a simple process which does not require vacuum, just for treating silicon wafers. For example, this is a Korean machine for atmospheric pressure CVD. So it's an industrial inline equipment. It's very large because you have a big transmission belt to convey the substrates from one end to the other. Now we have a system, a process which requires vacuum. It doesn't require very high vacuum. It's a low pressure CVD or AP-CVD. You can, for example, produce germanium quantum dots, for example, for emitting light, okay? And you start off with a precursor with a germanium gas. It has this form Ch4. And in order to break down this germanium gas, because you want to separate the hydrogen from the germanium, you have to have some kind of activation. This activation is from high energy radicals coming from hydrogen. So you make an inlet of hydrogen with molecular hydrogen into your chamber. When this hydrogen passes through this channel here, where we have an antenna with a very high frequency generator, so it will ionize the hydrogen to transform this to a plasma of hydrogen ions and the electrons, okay? And you need to have this power running throughout the whole experiment, so you're continuously generating the plasma. And afterward, these hydrogen radicals which are generated here, they are absorbed here on the surface, okay, of your substrate. You have here a silicon carbide heater, and when the germanium gas absorbs on the surface, these radicals will break down the GH4, and you will leave only germanium islands on the surface, which can be afterwards nucleated into germanium quantum dots. Here you can see the difference between zinc oxide coatings deposited here on the left by atmospheric pressure CVD, and on the right by low pressure CVD. So here involving some vacuum. Okay, both films are zinc oxide based. The ones on the left are doped with the fluorine, and the ones on the right here are doped with boron. So here is the surface, okay, of ZNO doped with fluorine and ZNO doped with boron, okay, and here is the respective cross section of the films. You can see that atmospheric pressure CVD, if you look at the cross section, so this is the substrate, okay, and this is the cross section of your film, and this is the surface of your film. You can see that the atmospheric process generate rougher films. So you will have larger crystals, okay, with a more three-dimensional growth, with varying size of grains. You can see small grains, big grains, etc. So this will give a very rough surface. Okay. Whereas here on the left side, on the right side, you from the AP-CVD, the low pressure CVD, you have films with a more finite grain sizes. You also have a random distribution of these three-dimensional type of crystals. They grow in columns like in sputtering. Okay, you can see here from both cases, they start off from smaller crystallites. They have this kind of island growth which develops into columns that you see here. And as the thickness of the film increases towards the surface, these crystals become broader, okay? And here, for example, you're looking, if you look at the Thornton model that I explained you on a previous chapter, you'll see that it's a transition between zone 2 and 3. You have these very large crystals that you see here, okay, which do not grow as columns from the substrate, but they stop somewhere in the middle, and you have a transition to zone 3 where you have these very large crystals. Okay, so there are advantages for these types of coatings. Of course, if you need to have a surface which has a lower friction, then you have to have a lower roughness, and this is then you would have to choose this type of coating. On the other hand, if you want to have a surface which can be abrasive for particular applications, then you will require the film surface with a higher roughness. But on the other hand, since these materials, zinc oxide is a transparent layer, and if you dope it with fluorine, normally it can become electrically conductive, and you can use this as a top electrode on some solar cells, which are transparent, so the light still continues to go down towards the active part of your photovoltaic material, and this is only an electrode, so where you can harvest the electrons which are generated from this process, okay? And when you have a rough surface, it's actually can be good, because if you have light coming in, okay, and as the photons enter this material, you have a very rough structure. You have lots of interaction between this material and the light, so it will scatter the light more efficiently, okay, and until it goes into your active material. And if the bottom part is metallic and it reflects light, then the light will go up and can escape. But again, when it passes here, since you have a very disordered structure, lots of grain boundaries, which can scatter the photons, then part of this light that is reflected can go back down, and you have a continuous process which is continuously activating the photovoltaic material. Whereas in this case, you have less dispersion, and so you have the higher probability of light after passing through this electrode part and reaching the active photovoltaic material. It can just leave, and then you will perhaps have a lower efficiency in the photovoltaic material. Okay. Now, this is a case of hot wall CVD chamber. And I saw one of these processes in Fayoum in Egypt when I visited the university, and they had this type of reactor which used some transition metals or alloys based on iron, cobalt, and nickel to actually create carbon nanotubes. Okay, and so how does this work? See, here you can see this cross section of the carbon nanotubes. You can see in one case you can actually see the height of them. Okay, it's 113 micrometers, and here it's 10 times the VAP value, and here they are more perfect. Okay, so let's look at how you can produce this type of carbon nanotubes. Okay, the CNTs. So you need to have a furnace, so it's a hot wall CVD. Then you have a quartz tube here. Okay, you have a quartz tube. You can have this with a small vacuum, or you can just do it at atmospheric pressure. So you have these coils which give heat, which will heat the quartz tube. You need to heat up to between 700 and 900 degrees C. That's why you use a quartz tube. Normally, a normal gas cannot withstand more than 500 degrees. So if you have a quartz tube, you can go up to almost 1000 degrees. And so you need to put a precursor gas. And the precursor gas is a gas which has carbon, okay? And if you can, for example, use methane, or you can use acetylene, and you can just feed this gas through a mass flow controller or mass flow meter, which you control the amounts of C2H2, for example, Ch4 that you put into your system. You need to have a carrier, a gas, inert, which is argon, for example, or sometimes you can just use air or nitrogen. And for some pretreatment, you need to perhaps give a small amount of ammonia. So all of these gases, they pass through mass flow controllers, which control each of the flow of these gases, and these gases go into your quartz tube, and they will pass here on your catalyst material. And so here you have your catalyst, which is, like I said, can be one of these metals or alloys of it, iron, cobalt, or nickel. And so when this precursor reacts with these catalyst metals, it will break down and it will form carbon. And this carbon actually grows in the form of nanotubes, okay? You really need to have to control the flow of these gases. For example, if you don't produce, if you don't introduce no argon, you have this disorder nanotubes, and they actually do not grow very tall. But if you put a little bit of argon, which is only 10 uh, standard cubic centimeters per minute, or 10 milliliters per minute, then you can grow more uniform carbon nanotubes and with much taller. Okay, so this is the nice example using a CVD hot wall reactor to produce carbon nanotubes. Here close by to where I am in Minho region in Portugal, but across the border in Spain, in Vigo, they have a nice setup for thin film germanium or silicon germanium deposition. They use the laser, and so it's a laser CVD. So you have the same process where you have to have a reactor and you have to input a gas inside, and here the activation is coming from the laser. Okay, so for example, if you want to produce germanium or silicon germanium, then you have to, for example, if you want to produce germanium, you have to put inside a germanium gas like the Ch4 that I mentioned a while ago. And so when the gas is fed and when it reaches the substrate, you're shooting a fluorine laser beam with 193 wavelength, and this laser will break down the molecules. Okay, you will have a fluence about between 25 and 100 millijoules per square centimeter. The pulse width is about 25 nanoseconds, and so the power, the density that you are applying is about, it's less than 2 watts per square centimeter. Okay, so if you want to produce germanium, you will use germanium gas. If you want to produce silicon germanium, you will have to introduce both the germanium precursor, which is the GeH4, and the silicon precursor, which is the silane, SiH4. And you can, of course, move here the sample position to accurately have the, the, the shooting this laser into the reactor to efficiently break down the precursor gases which are inlet in this system. And now let's take a look at an industrial machine to produce, for example, gallium arsenide, which is very important for in the semiconductor industry. In this case, it's a metal organic CVD, so MO-CVD. MO-CVD is used for the commercial production of group 3 and 5 and group 2 and 6 compound semiconductors. It has the advantage of using reactants that are very volatile, have a relatively low temperature, or at a relatively low temperature, and it's ideal, for example, for the deposition of polymer substrates, because if you do CVD on using polymer substrates at very high temperatures, then you will destroy the substrate. For example, it's unthinkable if, for example, you put in polymers here in this process, or some kind of, or other processes which are very energetic, because you will destroy the polymer and meat. So for the production of gallium arsenide, you will need two precursors. You will need a precursor which brings the AS elements, okay, arsenium elements, and another precursor which will bring the gallium. And that's why you will use ASH3 and 3-methyl gallium as precursors. And upon the reaction, and this reaction is mediated by temperature, you will have the breakdown of these two precursors into gallium arsenide plus methane. So you can recover this methane and use another process. So here is a schematic of how this works. You have a stream. So this gas stream is the ASH3 plus the 3-methyl gallium. Okay. And you will have a hot gallium arsenide wafer. So you will use actually a substrate, which is the same material as the material that you need to deposit, or at least a similar material. Okay, so you can use, for example, gallium arsenide substrate, and you can grow, for example, gallium nitride or gallium phosphide or gallium antimony or Indian gallium arsenide, etc. Okay, but in any case, so you will have these organic carrier molecules. For example, the purple are the ones which have the gallium atom. So this is 3-methyl gallium. Okay, and this precursor is this one. It's ASH3, okay? And when these precursors, they fly above your substrate, due to the temperature activation, they will drop these atoms, okay, in ordered form, and they will grow monolayer by monolayer with a high coverage and a very good coherence throughout the deposition of these layers. And you will have something like a monocrystal, okay, but on a smaller scale. Now you can see some CVD process which use a plasma enhanced reactor. So in these cases, you need to have something that breaks down the precursor and make this into a plasma. And this, normally you use an alternating current generator, so you can use a microwave generator here or a radio frequency generator. And this radio frequency generator will break down the precursor gas which is fed into the system through the reactor. And due to the generation of the plasma, the precursor is broken down and it absorbs here on the surface of your sample. Normally, if in this type of plasma enhanced CVD process, you are working at pressures around 0.5 to 1 millibar. So 1 millibar is 1,000 times lower than atmospheric pressure, and you normally have powers of 0.1 watts per square centimeter. If you compare this with laser CVD, these powers are much lower. Okay, so here you will have much higher powers using these layers of pulses than you have in this case. So it really depends on what type of precursor, because some precursors don't need such a high activation energy. But if you want to break down silane or germanium gas, you need to have a very high power density to break these precursors. Okay, so it really depends on what you need to do. Here's a case where we want to produce silicon dioxide and silicon nitride for these MOSFET devices that I showed you before. So, for example, to produce the silicon nitride layers, okay, and also to produce, for example, here the silicon dioxide insulator parts that you also see here, okay. You need to have normally the best option is to use this inductively coupled CVD. So this ICP CVD. So it's something actually similar to what I've shown you before for the low pressure CVD here. Okay, you will need to have an activation of the plasma using an external circuit. But here, remember that you are using silane, so you will need a higher activation energy. And so here you input the gas, you have this kind of coils here, which are an inductor. And this inductor is also can make a confinement of the plasma to the size of your sample, okay? So you can design this part here of the inductor so that the plasma plume that you will have will cover the whole substrate as you see here. So you will have a plasma generation here, okay? Which is important for the creation of radicals here. And then you have the nucleation of either silicon dioxide or silicon nitride thin films on your substrates. So one of the last, I think it's last process, and I will go into atomic deposition. So one of the last processes that I'm going to talk about is the hot wire CVD. And the hot wire CVD is very simple. You need a high vacuum chamber where you have a filament. You can see the filament here when it's heated up, okay? Now it's a tantalum filament, and it can be, if you pass a current of 15 to 17, 20 amps, you can reach a temperature locally of around 2,500 degrees C. So for example, if you make a gas inlet of silane, of hydrogen, or other types of gases, then when these gases, when they pass through the filament, they are broken down, you see. For example, here, if you take a look, if you imagine this is silane or methane, for example, then the silicon or carbon atoms are separated from hydrogen when they pass through the filament. And for example, you will have only, for example, the position of silicon, okay? Or only the position of carbon if you use methane, for example. Or only the position of boron if you use this type of gas here, okay? And normally you do this you have to have high vacuum before in introducing these gases. And during the deposition, the pressure can be, you have to start off at a pressure around 10 to the minus 7 millibar. So it's 10 billion times lower than atmospheric pressure. But when you introduce these gases, the temperature, the pressure will increase to around 10 to the minus 3 millibar, which is around 1 million times lower than atmospheric pressure. Okay, then you can produce the coatings. And here you have, you know, the position from bottom to the top. Okay, and in some cases you can produce also very large crystals, and which can be shaped as columns, as you can see here. So this is a schematic of one of these systems. For example, if you want to have here for this case, it's on the schematic you have a carbon source. Okay, so it's, for example, if you want to produce a carbon coating, but instead of using saline, you use methane, Ch4. So you have a carbon source, for example, methane or acetylene. Okay, and you have an inert gas, for example, argon, that will carry your precursor gas. Okay, so the gas is transported here to the hot wire. It's broken down to the heat of the filament. You have to have power supplies here for creating a potential, either for heating your substrate. Here this power supply, which is connected here to the substrate, it's only for heating the substrate. And this one is for providing a current that goes through the filament to break down for example, the Ch4 molecules. Okay, and you can have here a nitrogen precursor. For example, if you want to make a carbon nitride coating. Okay, you just put some amount of nitrogen precursor here. It can be solid material, and you will have carbon nitride. And then these are some applications. You can produce very nice coatings for example, flexible graphene transistors. Actually, most of the graphene which is produced in laboratory is done by CVD methods. Okay, so here you have a CVD graphene transistors which can be produced on polymers, or you can produce photovoltaic materials, for example, morphosilicon or cadmium telluride on top of polymers. You can go do this also by CVD, etc. And when you're producing coatings or films, for example, which have a high order of symmetry, where you actually cannot distinguish from going from your substrate to your film, as is in the case when, for example, you produce semiconductors by the molecular organic CVD method, and you have this such ordered material, then you cannot really see the difference between your substrate and your film. You can do this. You can just check if you have a good coherence between your substrate and your thin film. For example, if you use, for example, Photoshop or a software which you can use for making a Fourier transform of an image, or you can use, for example, I forgot the name of this software which can be used for treating images, imaging analysis. I really forgot the name. Starts with a J, but okay. But you can use a specific software, and you can, for example, have a region of interest of your sample. Okay, you just make here. You just get out a zone where you want to analyze, and if you go into the menu of the software, if you look for FFT, which is Fourier transform, and if you make a Fourier transform of this image, you'll transform it into this, and you can just check the straight lines to see if your material is coherent. So the straighter the lines, and if you have any defects, the better coherence you have between the substrate and your thin film. Okay. And for this case, we were using strontium titanate as a substrate, and also producing strontium ruthenium oxide. Actually, both are ABO3 materials which have a kind of perovskite structure, and they produce very nice ordered materials. And you can do this by metal organic CVD for that. Now I'll conclude my talk speaking about atomic layer deposition, which is another process of chemical vapor deposition, but it's more sequential. Involves the inlet of a precursor gas and the purging of the gas, and another type of gas to remove specific elements or molecules that you already have on your substrate. And so this is called atomic layer deposition. It is also a thin film deposition technique. It's based on the sequential use of chemical process in the gas phase. It is a subclass of chemical vapor deposition, and most ALD reactions they use two chemicals called precursors, which are also called reagents, as in the case of normal CVD processes. So these precursors they react with the surface of a material one at a time. You can pulse them. You can program specific quantity of molecules of these precursors that can go into your system and how long they will be active inside your reactor. And through the repeated exposure to separate precursors, the thin film is deposited very slowly, very conformal to cover the whole surface. And in most cases, you will have a very high coverage, and you will have also will have the formation of monolayers, which are really completed, and you will have stacking of layers, which can be done with different materials and very ordered. So ALD is a fundamental process in the manufacture of semiconductor devices, and is part of a set of tools available for the synthesis of the most recent interesting materials for semiconductor industry. Here you can see a comparison between physical vapor deposition and atomic layer deposition. Okay, so in PVD or sputtering or thermal evaporation, you will have a vapor flux. Either it's coming from the target or coming from a crucible. Okay, and you will have physisorption of the atoms that reach the surface. You will have a continuous flow. You will have some atoms which will have some mobility that will look for, they will look for preferential sites for nucleation, and you will have a thickness gradient, especially if you have large substrates comparing to the sources, or if you have three-dimensional substrates, not planar substrates. Okay. Whereas if you use ALD, you will have cycles. You'll have a cycle which you will be pulsing a precursor, which brings the raw material for the formation in the salt phase. Then you will have a purge of the non-reactants. You will have an oxidizing pulse, can be with ozone or can be with water vapor, for example. And you will have a purge. And you will do this repeatedly, sequentially, in order to produce something like a multi-layered material, okay, with a very high order. And so in ALD, you will have chemisorption, not physisorption. So this is a physical method and this is a chemical method, okay? There are self-limiting reactions which are related with the formation of the radicals that you have on the surfaces. And you will have a uniform distribution of the layers around your material that you want to coat. And here you can see a comparison between ALD, CVDs, and other processes of physical vapor deposition. I think this is post-layer deposition. It's another method involving similar to sputtering, but you have a laser that shoots photons into a target. It will remove material from the target, and then it creates a vapor, and it's also deposited. So it's some kind of physical deposition method. But anyway, you can see here from this graph the step coverage. In ALD, you have a very high step coverage. It means that you have a very good coverage of your substrate, okay? But the drawback is that the reaction rate is really very low. So here we are in ALD processes at the most, on the most efficient ones, we are producing 1 nanometer per minute. So you're producing 10 angstroms per minute, which is very slow. For example, if you compare this with sputtering, you can go up higher than 100 nanometers per minute, okay? But the coverage is much smaller. It can be below 50% of the surface, okay? And here you can see, for example, the formation of aluminum oxide, alumina, on a silicon surface. So you have a silicon surface which has this kind of wells, okay? And you will need to perform a coating which is conformal, okay? That will reproduce here this function of the surface, okay? And you can do this using, for example, 3-methyl aluminum, which is the precursor gas, which brings the aluminum that you need, okay? And you make a pulse of this 3-methyl aluminum. And so this 3-methyl aluminum absorbs on the surface here, for example, the silicon, okay? Then you will have to have a purge because you want to take away the hydrogen, okay? You only want to, in the end, you only need aluminum and oxygen. So you have to remove the hydrogen. So you oxidize the surface in another pulse with water vapor, for example, okay? And this water vapor comes in, it will, so you have H2O, okay? Uh, so these hydrogens can be bonded with, with the oxygen atoms here, and they will just leave out in the form of water. So remember that the blue dots here, the ones that these blue dots are the coming here from the initial precursor. So you have aluminum and these three methyl groups, okay? And in the end, you only want to keep the oxygen, which is these yellow atoms, and you want to remove these hydrogen atoms. And if you look here at the step, you see that there's a very good coverage, okay, of the surface, okay, and you replicate the structure of the surface. So let's take a look at this video, where you can see one example of the atomic layer deposition of titanium dioxide, okay. Sorry, hafnium oxide. So you do this also by atomic layer deposition. So here is where you have your reactants, and here your chamber. And in this particular case, we're going to make a coating of an optical fiber, for example, for the transmission of multimedia or transmission of light. And so here are your reactants. So you have to have a precursor which has the hafnium, and which is HFCl4 gas that is inlet in a pulse into your system. So the HFCl4, of course, will be absorbed on the whole exposed parts, not only here on the cores of the fiber optics, but also on the shielding. So the idea is that so you have this HFCl4. You have to remove the CLs, but it's easy because if you have hydrogen, then hydrogen will bond with Cl and will form HCl, and you can easily remove it. And then you continually bombard the surface with HFCl4, and on another cycle, you will be removing the chlorine ions, okay? So here what you deduce here, for example, is water vapor, okay? And this water vapor is important because you need the oxygen to bond with hafnium, and you need the H to bond with the chlorine to form HCl. And then in this process, you will have a sequential deposition of the HFO2 material, okay? As you see here, stepwise. And this can be done with a very good conformality of your material. Here, the position is also on the shielding material beside the core materials there. And so it's a very interesting process. And sorry, I forgot to check one last thing here. One last slide. Okay, now I understand. There was a slide also involving titanium dioxide deposition, and I just jumped around. So let me get it back. Okay, let's see if I can show it to you. So now this is the position of titanium dioxide. It's a similar process to the one that I showed you regarding hafnium oxide. So now you need a precursor for titanium. It can be, for example, titanium Cl4, titanium tetrachloride, which is your precursor. And you can make the deposition of this titanium dioxide on complex surfaces, for example, as is the case as this video. The titanium dioxide is a very interesting material because it's a photocatalytic material. So here you need to have some radicals on the surface, and then you bring down your precursor, which is the titanium tetrachloride. So you need to keep the titanium, but you want to remove the chlorine. The same process. So you have to then on another pulse oxidize the surface with water vapor. So the hydrogen will bond with the chlorine ions, they will form AgCl, which can be removed out of the system. And the oxygen is needed to bond with titanium to form the titanium dioxide. If it is in the anatase form, then it's a body-centered tetragonal material, which has very interesting photocatalytic properties, which can be self-cleaning, antibacterial, can be also used as a photoanode in some photovoltaic systems. And so then you have your surface coated with the titanium dioxide. So this is what I want to show you. Thank you very much for your attention. I will be scheduling a specific time in the agenda so we can discuss these slides. If you have any doubts, if you have any questions, I'll be very happy to answer them for you. Thank you very much for your attention, and see you.